Good afternoon. Thanks for your patience. Hello. Want to welcome you to this session for Designing with TM30. And we've got two amazing speakers. Tony Esposito, who is the founder and head research scientist of Lighting Research Solutions, a lighting consultancy providing services in research, education, and development. Tony holds a doctorate in architectural engineering from Penn State University with a minor in statistics. His specialties include color science, color discrimination, IES TM30, human factors research methods, circadian metrics, and spectral modeling and optimization. Other speaker is Jason Livingston, who is the principal of Studio TNL, which has dual specialties of architectural lighting design and theater planning and design. Jason has been teaching lighting design in New York City since 1993. He currently teaches lighting design at New York School of Interior Design and New York University, and has taught at Pratt Institute and Fashion Institute of Technology. He has earned numerous awards for his lighting work. So I want to welcome first Tony Esposito.
Great. Is my mic working? Oh, yes it is. Hello everyone. Can everyone hear me? Yes, sir. Perfect. All right. Great, great, great. Thank you for being here. This is, I think, the last session of the whole conference, so let's close it out with a bang. So my name is Tony. My co-presenter here is Jason. We're both members of the co-chairs of the IES Color Committee, and so we're going to talk about today what is my favorite topic, which is color science, and probably one of Jason's favorite topics too. So here's the mandatory AIA statement. What we need to do first is one of the most important things. So all of this has happened because of the Dallas Market Center and ETC. So we're like, seriously, we're very grateful for both of these entities. So what I believe what you're gonna see today is a TM30 demo, a live interactive demo of this stuff. And it is, in my humble opinion, the best one that has ever existed and the best one that probably ever will exist. And that's only because of these two groups of people right here. And so we owe them a debt of gratitude. So the session today is going to be split into three parts. The first part is going to be me talking mostly about the science and technical aspects of TM30, hopefully in a way that's not too dry or boring, but in a way that I think is important that we at least understand a little bit of how things work before we start using them. Jason's going to talk about TM30 in the context of design and application. And he's going to talk specifically about something called Annex E, which is based on the table in front of you. The table, not the table, this table. So he'll talk about that. And then the third part is we're going to take all of that. That should last about an hour, and then we're going to go over into the demo room and spend about 30-ish minutes looking at this stuff in real time. So with that being said, our main goal today is to sort of start with the baseline, try to understand how some of the metrics are put together, why they matter, try to understand how we might use them throughout the design process, which Jason is largely going to tackle. And then really with the demo, what we're trying to do is take those numbers that can sometimes seem benign or difficult to use, but then connect them directly to our visual experience. So we're going to try to bridge the gap between the numbers on a page and the physical, real-life experience that we'll get with these things. Hopefully to convince you that the lighting color people of the world aren't just making up some numbers to try to make things look harder, but that it really works. And so that's our goal here with that. So we're going to start with the background, the technical part of the talk. So this is a spectral power distribution. Fancy words for saying this is sort of the light source's fingerprint. This is the amount of radiation or power in each of the visible wavelengths in the visible spectrum. So 380 to 780, there are more wavelengths on that side, shorter, and more wavelengths on this side, longer. But this is the special range of radiation that our human eye is specifically tailored to see. It's very special in that way because there's lots of radiation we can't see. Actually, we can't see most of it, but this part we can. And each of these wavelengths we sort of interpret differently. We see the short wavelengths to be bluish, the middle wavelengths to be orange and yellowish, or green and yellowish to orange, and then in the long wavelengths we see them as red. Okay? Does anybody know what light source this is? Incandescent. Beautiful. So the incandescent, long, broad, energy in all wavelengths. We could also start to derive some information from the SPD. We see that on balance, there's a lot more long wavelength radiation than the short wavelengths, which is why we tend to perceive it as warm, right? So we're going to see that all color science, all of the things we talk about today, all of the fancy measures, they all start here at the spectral fingerprint, okay? This is going to dictate all of the ways that it impacts color. So just to give some examples, so the spectral fingerprint, so once you sort of like understand how SPDs get generated through lighting technology, you can start to recognize those technologies in that spectral fingerprint. So these are phosphor converted LEDs at 2 different CCTs. PC LEDs start with the blue chip, smother some phosphor over it, that down converts some of that radiation, and you get this blue peak and this big hump, very characteristic of a PC LED, and it's the ratio between that blue and the hump that gives you the CCT change, at least in some of the older ones. This is an RGB LED, where you take discrete individual emitting diodes and you mix them together to try to get white light. This is just a couple examples. All of the light sources you're going to see today are this kind of discrete color mixing setup, because we're using theatrical fixtures from ETC. Then you got your incandescent, your old school fluorescent, and then furthermore, high pressure sodium and ceramic metal halide, right? And those jagginesses come from sort of amalgams under high pressure. Right? And so we had a student session earlier today, and I was like, I don't even think they know what some of these light sources are. Do they? I don't think they know what a ceramic metal halide is. So, it's funny history. So one of the important things, so as I mentioned, all color science, a lot of the things that we do over here on the color science side, we start at the SPD, and what we do is we filter them through this black box, right? It's not a black box for me, but inside this black box exists calculus, color science, color spaces, vision metrics, right? All of these fancy things. And that's sort of my job to understand. But from the lighting practitioner side, all you really need to do is to focus on the stuff that comes out of the black box, right? And how to interpret it and what it means and how to use it. And so that's where we're going to focus all of our attention today, is how to interpret what comes out of those black boxes. I'll give like a little insight into the black box sometimes, but we're not going to focus on things like color science and how to calculate color difference and all the fancy vision metrics. We're going to focus on things like metrics in TM30 and how to use them and what they mean, how to interpret them, okay? So just to sort of blow this up a little bit and list a lot of the stuff that comes out, one of the first sets of things that comes out of the SPD is the most familiar metric, I think, CCT, the color appearance of light. So, which is to say, we're not considering any objects yet, we're only looking at the color of the light coming out of the fixture on a scale of warmness to coolness. And another metric that's less known but equally as important is the tint of that light along the pink or green scale, okay? So you could have two light sources with the same CCT but different DUVs, and therefore they look different. We could do a whole course on that, but unfortunately we don't have time to talk about all that, so I have to leave that conversation there, but I'm happy to answer more questions later. Then the second set of things is TM30. This looks complex and it should make sense later, but measures from TM30 come from the SPD. The relationship and specification structure for relating measures of TM30 and repeatable visual outcomes is related to Annex E of TM30, which is this, and Jason's going to talk about that later. And then, just to mention it, there are other things that come from the SPD, other color rendering measures, some of these two that I've participated in building, but we're not going to talk about any of that. It's just to show you that as complicated as color is going to seem today, it's even more complicated. So, but hopefully we'll get most of it done today. So the transition of light, I think, is pretty easy to understand in concept. A light source emits light. That light has this spectral fingerprint built into it, right? It emits light with different radiation, different wavelengths. When that light hits an object, that object absorbs some of those wavelengths and reflects other ones, right? It's the ones that are reflected from the object that come into our eye and we make an evaluation. That looks good, that looks bad, that red doesn't look right, something's off, right? To think about it more technically, the light source has that spectral power distribution. And objects have a spectral reflectance distribution. These are the wavelengths they like to reflect to us. And then when we combine them, we get the radiation that actually comes into our eye. And hopefully see now why we perceive that red apple to be red, right? Because it's reflecting those long wavelength radiations into our eye. But we can do a little bit of a thought experiment and say, what happens if I take my light source, this case the incandescent, and I can filter out all the red radiation, right? And then I light this apple. What does the apple look like? Black, right? If you take all of the radiation that the apple likes to reflect away from the apple doesn't reflect anything to us, okay? So what this means is that color is not an intrinsic property of objects. The red apple is not actually red, right? Color is a human visual experience, right? It's a human visual phenomenon that depends both on the light source and the object, okay? That's important to understand. It's not intrinsic. The red apple is not really red. Red is a perception we have under a specific context. But as you'll see today, we can change that context and make things that we think are red not actually red, okay? So color is not intrinsic to objects. So, with your mind thoroughly blown, we can start talking about color rendering. So, color rendering. What is color rendering? So, I'm going to pull up a definition here. So, the International Commission on Illumination, the CIE, is the organization that standardized and maintains CRI. And this is how they define color rendering. And I'm going to read it verbatim because I think there's some important concepts that we're going to have to hammer down. So color rendering is the effect of an illuminant on the color appearance of objects by conscious or subconscious comparison with their appearance under a familiar reference illuminant. Okay? So when we're talking about color rendering, we're really talking about faithfulness of a sort to a reference. Color rendering is not absolute. It's not on an absolute scale. Things aren't better or worse. They are something related to a reference. We're always doing a comparison, right? And we're going to see how that plays out. So color rendering is relative, always relative to something else. And so I've said, Jason has now heard me say this multiple times, if you take nothing else that I say away from today, you forget everything, I want you to remember that color rendering is relative because it's the baseline thing that makes understanding all of this stuff possible. We have to, this is our foundation. We have to start here understanding that color rendering is relative. So just to drive the point home, make the text a little bigger. It's relative. And then in case you still don't got it, relative. And then if I say it a bunch more times, maybe you'll get it. So it's relative. This is a really fundamentally important concept. So instead of saying for like with CRI, instead of saying, well, is that a good CRI or a bad CRI? Or is this a good gamut area or a bad gamut area? Instead, what we could say is, what does this metric say about our light source relative to its reference? That is the whole thing, right? This has to be the baseline because this is how it's done. This is how the calculations are performed. This is what the numbers tell us. So there are two major concepts that we need to get really comfortable with to understand a lot of the color rendering metrics that we're going to talk about. So, okay, we're in Texas. What's the capital of Texas? Austin. Surprisingly, everybody has known that so far. I had to Google it. I'm from Philly, so I was like, what's the capital? When I was making this graphic. A little embarrassing, but you know. We're in Dallas. How far are we from Austin? We're going to call Austin our reference point, right? So like we would have a reference illuminant, we have a reference point here. 5 hours? What else? Anybody, any other guesses? 5 hours, 3.5?
3 hours, 6 minutes.
3 hours. He's seen this presentation 4 times now. So how far are we? I don't know. Google says 3 hours, 6 minutes. You're a minute off. Come on. 4 times the charm, right? So this is our magnitude. How big of a difference there is between us and the reference point, right? Magnitude of difference. In this case, our magnitude is measured in miles or hours, right? Distance. In color science, our magnitude of difference is, say, units in color space. Difference between the test and the reference source, which we'll talk a little bit about, okay? Magnitude, how big of a difference is the first important concept. The next question is, in which direction are we right now relative to our reference point? So if our reference point is Austin, where are we relative to it in direction? Northeast, yeah, exactly. So if we want to just be super technical about it for no reason, we could say we're north, slightly east, or we could say 75 degrees north of east, or we could give polar coordinates, and right? But direction is the second important concept. Now we can fully describe our location relative to Austin. We're a certain distance away and in a certain direction. Magnitude and direction are the two major concepts that we're going to need to understand to interpret all of the metrics we talk about. So as a quick example to set the baseline, we could talk about how CRI is calculated. So here's our test source, or the light source we care about, right? And we imagine that it illuminates these different 8 color patches. This is the color sample set for CRI. Some problems with it you could probably notice already. There are only 8. They're all pastel. There are no red. They're not spectrally optimized. They're sensitive to individual changes such that they could be spectrally optimized. So, but we won't talk much about that. That's a whole other set of topics. But we imagine that this light source is lighting those, and then we compare it to its reference source, remember? Relative to the reference. In this case, in almost all cases, the reference source is going to be a broadband light source at the same CCT. There's some nuances in how it's calculated, but generally speaking, if you have a light source at 3000 Kelvin, your reference source is going to be a broadband light source with energy at all wavelengths at the same CCT, okay? And when you get higher up, you start using models of daylight. It's complicated, but broadband light source at the same CCT is all we really need to understand. And what we do is we calculate the difference, the magnitude of difference between the test and the reference source. And then you average them together. 1 plus 2 plus 3, and then divided by 8. So like an incandescent is a broadband light source. In the SPD, so it contains radiation in all of the wavelengths, right?
But if it's a CCT to 3000, it's not broad.
So like if we used, so incandescent is a type, it simulates black body radiation, and black body radiation says that we can look at emission based only on color temperature. So if I have 3500 Kelvin, it might be like the incandescent, just tilted a little bit to have a little more blue, right? And then if I go to 4000, it's going to tilt like this and have a little more blue. But it's broadband, it has energy in all wavelengths. Yep. So like for example, an incandescent is 2700-ish Kelvin. Its broadband reference source is almost identical to the incandescent. So incandescents almost always have a CRI of 100 because they are basically their own reference. It's a funny little trick for them. So that's it. So what this means is that CRI only tells us, on average, how far we are from the reference. Magnitude information only. How far are we from our reference illuminant? It doesn't tell us direction. And we're going to see that direction is critically important information in color science and in color rendering. So let's imagine this. We have a perfect fidelity, which would be to say the color rendering index is a fidelity metric, faithfulness to its reference. There's a synonymous metric in TM30 called RF, which we'll talk about. And so perfect fidelity would be CRI 100, RF 100. And we light these objects. They look pretty good. Like if we walked into a grocery store under CRI 100, we'd probably find it acceptable. It would be okay. But we can deviate from that reference source by increasing the saturation of objects or decreasing the saturation of objects, direction information, but so long as the magnitude of the difference is the same, color fidelity metrics can't pick up the difference because it can only capture magnitude information, right? And what we'll see over and over again, the research shows this, and I think you'll agree once you see it in person, people really like this increase, and people really dislike the decrease, okay? And then another thing you could do is you can hue shift objects by making them a little greener or a little pinker. And again, so long as the magnitude of the difference is the same, color fidelity measures like CRI cannot pick up the difference because it just isn't built that way. So there are all of these different ways that we could deviate from the reference, in some ways that people like and in some ways that people do not like. But again, so long as the magnitude is the same, color fidelity measures can't tell us the difference. So what this means is that one metric is not enough to use in specification or to predict how we're going to perceive objects in a space. It's not enough. So I find it helpful to step through the creation of some of the pieces of TM30, believing that I think it's going to make them a little easier to understand. So we're going to do that right now. This is the color space of TM30 with its 99 color samples. It has 99 that are very specifically chosen. They cover color space. There's a lot more of them. They're statistically chosen. They represent all possible colors. It's a very robust sample set. You don't need to know all of the inner details except that there are 99 and they were chosen on purpose, right? And you're seeing them here in color space under the test source, right? Under the source we care about versus the reference source. Now, remember I said that direction information is critically important in color rendering? The reason is that in color space, saturated colors live on the outside of color space. And desaturated colors live on the inside of color space. So if I have a light source that pushes objects outward, that light source is causing them to increase in saturation. If I have a light source that's causing them to shrink or push inward, that light source is causing them to desaturate. So directionality information is critical in color rendering. So if we take those sort of color shifts and vectorize them, we see that they all point inward. This light source is causing drastic desaturation of colors. Can anybody guess what this light source is, by the way? If you don't know, I'll give you a couple rounds of slides to think about it. So what we do is to make this thing a little easier to understand, because even as a color scientist, like I can't really make ready-made decisions based on the information in the left graphic, right? So what we do is we slice it up into a pizza into 16 slices, labeled 1 around 16, where 1 is into bins, and bin 1 is red. So in the same way that when you hear R9, you think red right away, in TM30, when you hear Hue bin 1, that's red immediately. So that'll be important. So here what we do is we average those differences, and we take the actual area inside. So this is Gamut Area, in case you've ever heard of Gamut Area Index, GAI. There's a Gamut Area Index in the color quality scale from NIST that was popular for a bit. And it's no more than a literal measure of area. So if I draw a triangle and it has area 10, I draw a bigger triangle, it has bigger area. And so why that matters is because in color space, where directionality matters, the bigger the gamut area, the more colors get pushed out. The more they, on average, increase in saturation. When gamut area compresses, colors move inwards in color space, where on average they desaturate. Right? People don't like this. So that's what gamut area can tell us. So gamut area of 100 means the same area as the reference. Greater than 100 is an average increase in saturation, less than 100 is a decrease in saturation. Okay? And then this is just another way to show this similar idea. This particular light source is compressing the gamut, causing a massive desaturation of colors. Okay? And then to make this a little bit easier to understand, we take the reference source and we force it into a circle. And we do that because it makes it a lot easier to visualize, a lot more easier. So what contained in this graphic is something called Chroma Shift. Chroma being sort of chroma or saturation shift. And so we can see RCSH1, Chroma Shift in Hue bin 1 is talking about the saturation of red, because Hue bin 1 is red. And in this case, negative 48%. A negative means desaturation, and 48 is massive, right? This is direction and magnitude information. Positive 11% up in the CS5, that's green. So this light source is basically desaturating all colors except for yellow-green. What's high pressure sodium? High pressure sodium, close, yeah. So, perfect. So, did you start Googling it? Oh, smart. Yeah. He cheated a little bit. He remembered the old slide. So this is a high pressure sodium. And so we don't really need TM30 and its complex metrics to understand that high pressure sodium was terrible at rendering colors, right? But now that we can see it's sort of mapped out, we know exactly why. And it's because it basically desaturates the colors of everything, except for this like narrow range of like yellow, this yellow-green. Yeah, exactly. And so this, I think, is one of the really powerful tools of TM30, is this color vector graphic. So this is sort of an overview of TM30. You have the fidelity and the gamut. You have this achievable range of values and a set of unachievable values just determined mathematically impossible. So there's this dovetail shape, right? Where do you think that dovetail comes from? Think about what it means to have an RF of 100. So an RF is 100, what happens? Relative to your reference, you are perfect match. Perfect match. There's only one way to perfectly match something, right? And so that's why there's only one point. But as you relax your fidelity criteria, say, you allow yourself to deviate more and more from the reference illuminant, you increase the number of ways that you can deviate, right? So that's why as fidelity decreases, the range of achievable gamut increases. So as fidelity decreases, the range of RG increases, the gamut area, where greater than 100 is an on average increase in saturation, and less than 100 is on average decreasing in saturation. That's because of the sort of expansion and compression of the gamut area in color space. Does that make sense? And then lastly, we have the color vector graphic, which exists at any point in there, because RF and RG are average metrics, and the Chroma Shift measures are exact, right? RF and RG can't tell us about specific colors. The color vector graphic can tell us exactly what's happening to specific colors. So, as a quick quiz, how many metrics are in TM30? I got 2. 2. Well, RF and RG are 2, and the color vector graphic contains 32. 34. Okay, the answer is at least 149. So get to specifying. If you start now, you might be able to figure it out in a year. No, so TM30 is sort of a methodology. It's a framework. And a lot of these will end up being useful for people like me, who do science and research and study. But we obviously don't need 149, right? It's impractical. You can't specify 149 metrics just for color, right? Nobody's going to do that. It's not possible. Also not necessary. So we should ask the question, well, how many do we need to consider? We know the answer is not 1, right? Because there is no one metric that can do it all. And we know fidelity can't do it on its own. So we need to think about what's the balance between simplicity and accuracy. We want it to be easy to use, but it needs to be useful, right? So what do you think that might be? How many might it be? 7. I thought I heard 3 somewhere. 3? 4? Okay, so the answer is 4. That's what the research tells us. And not necessarily all at once. So take a deep breath. It's better than 149. Oh, okay, so sigh of relief. Yeah, thank you. It's not going to be 149. I think if it was 149, everybody would just walk out of here. It's like, yeah. So no, the answer is 4, and I'm going to quickly summarize what they are. Most of them I've already mentioned. So we have RF. This is TM30's conceptual equivalent to CRI, except it's more modern, based on better science, more robust. It's less able to be like gamed, so you can't achieve an artificially high score even if your light source isn't great in the way that you can with CRI because it's a small sample set. So it's the conceptual equivalent. It tells us on average how far we are from the reference, but it's still only magnitude information. And one of the things that I find helpful is to think, like in a world where we only consider color fidelity or CRI, it's easy to get into the mindset that higher is better, right? And so we live in a spec world where the goal is to just push the number as high as possible, and higher is better in that way of thinking. But actually, according to the way it works, higher is just closer, right? Higher means you're closer to the reference illuminant. That's not always the best light source for all applications, as we're going to see. And so higher is just closer, not necessarily better. So that's important it helps me to think about. We have our gamut area, which is conceptually similar to other measures of gamut area that you may or may not have heard of, one of them being QG from the color quality scale from NIST, or the gamut area index from the Lighting Research Center. And so gamut area tells us on average, are we increasing the saturation of objects or decreasing the saturation of objects? okay? But it doesn't tell us which colors. It doesn't tell us if it's red or orange or green or blue being impacted, just on average. Our third metric is RFH1, so F being fidelity, and as I mentioned, anytime you hear H1 with TM30, think red, right? Red is in the human one. And this tells us magnitude information, again, but just for red. So we can tell if we're closer or further from our reference illuminant, but it's not telling us saturation information. And this is conceptually similar to R9. Okay, so similar to a CRI, R9 is just telling you magnitude information. How close are you to your reference? It's not telling you if it's going to look good or bad, because you could have the same R9 and one look good and one look bad. So it's important. And then lastly, I think where TM30 shines is with those Chroma Shift values, because it's telling us exactly what's happening to specific color ranges. Are those colors being increased in saturation, decreased in saturation, or no change? And we're going to see, and those are built into the color vector graphic, right? So when you see those arrows pointing in and it says negative 20%, that's the Chroma Shift value telling you that that color is being decreased in saturation. So as an example, what you should see, just to check, on the left you should see a desaturated apple and an increase in saturation as you move right. And if we say that the middle one is the one that is matching the reference illuminant, and we assume that these are all equally different, we see that the fidelity metrics can't pick up that difference in appearance because that's a direction change, and the magnitude is the same, right? So our RFH1, which is again equivalent to R9, can't pick up that difference. But that difference is important because people like this and people dislike this. And so the color fidelity measure cannot pick up that difference. That's where Chroma Shift comes in, which tells you exactly what's happening. Exactly, which direction exactly. So when you have a perfect match to your reference, there's no change, 0%. As you increase saturation, you get a positive percent. As you decrease saturation, a negative percent. It's a measure that tells us exactly what's happening to the colors. This is the power of TM30. So, quiz time, and then I'm going to pass you over to Jason. Ready? Let's test your knowledge. Okay, so I have a light source with an RF87. Ignore the left for now, just RF87. What do we know about that light source? Magnitude from reference, that's fidelity. Yep, color samples. Yep, so.
On the negative side, on the left side, if we're the decrease,
So
we say that?
we're not there yet. We're not there yet. We're on the right track here. Okay, so average magnitude from the reference for all of the 99 color samples. Okay, what about the number 87 itself? So it's not a percentage. It's not a percentage, but essentially that there's, yeah, well, there's no units, right? So it's like, I know, it's, exact, there's no units, right? Exactly. So it's sort of, all we know with that number is that there's some deviation. That's it. That's the whole thing, right? That's the answer. We know that there's some deviation relative to the reference.
How do you not have a unit? Like, how do you measure it without, like,
There are units for the color differences, but they're in color space units. But then with the averaging of the differences, you lose the unit information. Yeah. In getting it into a getting it in a way that's easy to understand for specification, we lose some of that information. But what's important here is this is the same thing as like a CRI 87. You don't know good or bad. What you know is some deviation based on the number. So we know 87 is less deviation than RF 60 and more deviation than RF 95, right? But that's it. That's all we know, right? So what if I tell you now that this light source has an RG of 109? Now what do we know? More saturated. Did you say? What did you say? What's that?
You know the direction.
We a little bit, yeah, we do. It's greater than 100, so we know that there's some increase in saturation on average. We don't know which colors, right? So greater than 100 is a bigger gamut area than the reference. On average, things are pushed out, but we still don't know what. Is it red or orange or green or blue? Okay. What do I know now? Particularly about Hue bin 1. Hue bin 1 is red. It's got a plus 11% for RCSH1. And we can see that the reference illuminant is in black, the test illuminant is in red, and is being pushed outward. What does that tell us? The red is more saturated. This light source increases the saturation of reds relative to its reference illuminant. And then it also does so for lots of other colors, as you could see on the vector diagram. And then one other point I want to make here is that in order to be if you're a perfect match to your light source, then your color fidelity is 100. There's no deviation. The second you have any increase in saturation or decrease in saturation, you're obviously no longer a match to your reference, and then your fidelity has to drop. It's part of the game, right? So RFH1 being less than 100 is because if the saturation is not 0%, fidelity has to drop, right? So if you increase saturation, like R9 has to go down. Doesn't matter. Penalizes all deviation, right? Even if we'll see that some are liked more than others. And then lastly, we see that this light source also increases the saturation of greens in Hue bin 4. Actually, that's 6. And so, does anybody know what light source this is? This is a hard one. I'll tell you that. This is a hard one. What's that? Metal halide. No, not quite. I heard a halogen. Is that what you said? So it's similar to a halogen. It's actually a filtered type of halogen, filtered with a neodymium filter, neodymium, which is famously known as the GE reveal lamp, the original GE reveal lamp, right? Which, as I understand it, was a very popular light source. Despite having a CRI of like 72, right, which is in this monolithic color fidelity world would be a bad light source. But in fact, people liked it because it increased the saturation of all of these colors and sold pretty well, as I understand. So we could see now why exactly that light source was good, because it did something that people like. All right, now I hand it over to Jason to talk about less technical and more design stuff. Hopefully your heads aren't spinning. Thanks.
All right, so that was your color science lesson for the year. Hopefully it wasn't too painful. So when TM30 was released in 2015, we knew that it was the most scientifically accurate, scientifically up-to-date color rendering system, right? I mean, all the components that went into it, the color space, the model of human vision, all of that stuff, we knew that was up-to-date and accurate. We were able to pull an enormous amount of information out of those calculations, right? We got 149 measurements. The thing that we didn't know at the time was which one of those are valuable and meaningful, and which one of those, you know, do designers want to know about, and which of those are perhaps not useful at this time. 2015, we released TM30. By 2018, a number of researchers around the world had taken this and had put it through its paces with human test subjects, right? And at the end of that time frame, I'm thinking like early 2018, middle 2018 now, we had a number of studies. We were able to select the 5 most high quality studies, and from those do, I suppose, what we would call a meta-analysis, right? And taking a look at the questions that were asked, the information that was gathered, and how can we synthesize all of that to draw some conclusions about what is meaningful within TM30. So I should turn a little bit so I can see, right? From those 5 studies, what we came away with was that we can do more than just measure fidelity with TM30, right? At the moment, there are 3 different aspects of color rendering that we can accurately measure and say something about. And I say at the moment because Tony showed you at the bottom of one of those early charts that We're looking at a measurement for metameric mismatch. We're looking at a measurement for color discrimination. What he doesn't show is that we're looking at a measurement for skin fidelity or skin rendering, and which might be different from other objects, and we're looking into that. So over time, TM30 may add more components, but at the moment we've got these 3 components of color rendering, what we call our design intents. And those design intents are, first of all, preference, second of all, vividness, and then we leave until last, fidelity. So, we said earlier, Tony mentioned that there were 4 important measures, and I just want to recap those important measures, because within Annex E, which is where this preference, vividness, fidelity, design guidance is provided, we're referencing the studies that are within TM30 Annex F. So if you wanted to, you could download it, TM30, it's a free download from the IES. Annex E is going to give you the information that I'm talking about. If you want to dive into the research that underpins Annex E, go read Annex F, okay? It's there for you. But what are those 4 measures? The first one is RF, our fidelity measurement. And I often find it helpful to read this RF and some of these other things as rendering subcategory fidelity, right? And in this case, what we're looking at is the global value. The next one is RG, so rendering subcategory gamut. And again, in this case, we're looking at the global value, not any specific color, but just on average, are colors being increased in saturation or decreased. The next one is, again, rendering subcategory Chroma Shift, subcategory Hue 1, which, as Tony pointed out, is red. So we're looking at the chroma shifting of red. Is it made more saturated or less? And then the fourth one is the fidelity of red, right? And the way in which it may or may not deviate from the reference. So with those 4 measures alone, we're able to say a great deal about a light source with regard to the prospect that it renders colors in a way that is preferred, that it increases the vividness of colors, or that it is a faithful reproduction of colors relative to the reference light source. So let's take a look at each of these 3. We're going to start with the one that's most familiar, fidelity, right? So we all know that when we talk about fidelity, we're just asking the question, how well do we match the reference? And high fidelity means that it's a really close match. As Tony pointed out, fidelity measurements penalize all deviations. They penalize all shifts. And so it sort of sounds as though what we're saying is, oh, CRI is no good, which might start to suggest that we think that fidelity is no good. That's not the case. And there are plenty of applications where high fidelity really is or should be our color rendering goal. A great example would be in medicine, right? You go to the doctor, the color of your skin, the color of your lips, the color of your nail beds, the color of fluids and tissues, that's all meaningful information to a healthcare provider. We don't want a light source that's going to go distorting all of that, right? So that would be bad. Fidelity absolutely has its place. The next design intent, preference, is one, it's sort of an umbrella that has to do with things such as acceptability, pleasantness, things like that. And I'm often asked when I'm doing a presentation like this, whose preference, right? Is it my preference? Is it Tony's preference? It's not. It is everybody's preference. So how do we know? Because we've got these 5 studies. So imagine you've been recruited to be a test subject in a color rendering study. You come in, one of the researchers says, look at this scene, explains to you what high fidelity is, tells you this is a high fidelity scene. You say, okay, great, got it. Researcher gives you a different SPD and you say, oh, wow, so some of those colors changed. Can you go back? Okay, go forward again. Yeah, they definitely changed. I gotta say, I like this one better than the high fidelity. Okay, if that happens once, it's an anecdote, it's a data point, who cares? But when it happens repeatedly over the course of 5 studies with 5 different groups of researchers in multiple countries, Now we have some real data. Right now we can say, broadly speaking, people find this light source preferable, not just Jason or Tony finds this light source preferable. So that's where this comes from. And really what it comes down to is that people like a light source that causes a slight enhancement of chroma across the board. So that's one of the things that we're targeting as we're looking at RG, right? And that's an important component in determining whether or not a light source is preferred, which is to say, you know, we're allowing, and in some cases even rewarding, deviation from the reference. And there are lots of places where this might be an appropriate applications such as retail, hospitality, maybe residential, are places where it's quite possible now that preference is a design possibility, that this is where you want to go rather than high fidelity. The next design intent is vividness, right, which is about asking the question, is this a light source that increases chroma? And that's really what we're asking. We're not asking, does it decrease? We're asking, does it increase? Does it make things more vivid? Over time, I think that in anybody's career, it's likely that vividness is going to be the least used or the least relied upon design intent, but it certainly has its place. If I were lighting a Skittles store in Times Square, forget about fidelity, right? I want colors leaping off of those candies. And so I would be looking for a high vividness light source. It is important to keep in mind that vividness is definitely distorting colors. And at the highest level, colors may become cartoonish, perhaps even to the point of being disturbing or unattractive. So there is color distortion that we like, then there's maybe a gray area, and then it's Technicolor and it's cartoon, and maybe we start to pull back a little bit from our appreciation of that color change. And we can push color change much, much, much farther than we would find acceptable in sort of a general lighting application. But it does have its place, perhaps in display, perhaps in retail, perhaps in entertainment. Okay. Here's some examples of what it is that we're talking about. High fidelity light source, great. The pizza looks like pizza, the basil looks like basil, the wood looks like wood, right? Say, okay, great, so this is exactly what I would expect. What's the problem? No, there is no problem. This looks great. This looks better to most people, right? By boosting the saturation a little bit, particularly focusing on boosting the saturation of reds, we get, this actually looks a little yellow to me now, this might not be the world's best projector, but what we get is that slight enhancement of chroma that people find appealing. This might be preferred, and this might be going too far, right? In this picture, what appear to be tomatoes in the high fidelity seem like maybe they're red peppers under the high vividness, right? So we're distorting colors to the point where perhaps we are misidentifying objects now. So we definitely can take the vividness too far, but this is an example of what we're talking about. There's another interesting thing that happened in the data. I'm not going to read all of this stuff to you. You can read it for yourselves. There's an interesting thing that happened in the data, which is that there were places where it seemed like there was kind of a natural break. And so as we're looking at this, it began to seem as though not only are we able to present three design intents, right? Preference, vividness, and fidelity. But maybe we can look at cross sections through there, and maybe there's a way that we can do essentially highly likely to meet that design intent, likely to meet that design intent, and then I don't know what the next step down would be, probably meet that design intent. And that's why each one of these design intents has three what we call priority levels. Priority level 3, it's not that you're not going to meet that goal, but you are less likely to meet that goal than if you had a light source that qualified for a priority level 2 or a priority level 1. You have this card, right? So these are all of the values for each of these 9 priority levels and design intents. And when you look at them, you'll see that essentially as you move up in priority level, the values become more restrictive, right? So if we look at the Chroma Shift of red at priority level 3, the range is from negative 12% to positive 18, but by the time you get to priority level 1, it's negative 1% to positive 15. The other thing that's really exciting about this is that we can have spectra that qualify, that meet more than one design intent. Which means that under the right conditions, I can have a spectra that matches or that meets priority level 3, preference level 1, vividness level 3, fidelity level 2. So we can, depending on the spectrum that's available to us, sort of mix and match our color rendering goals. We're not limited to just one color rendering goal going forward. It's not as though it's fidelity or nothing, right? It's fidelity and then we can scale it. Vividness and we can scale it. Preference and we can scale it. Couple of things to keep in mind, though, things that we may find going forward coming out of manufacturers, which is that higher priority levels may have a lower efficacy. And that really has to do with the fact that today the way we make white light is we start with a blue pump, right? A blue pump LED, you put phosphors on top of that. The phosphors then sort of down convert that high energy wavelength to lower energy wavelengths. So if we're going to take a blue LED and then downshift all of that energy into red, you're just losing energy and you're losing energy efficiency. So we may find, for instance, that we can have a fidelity priority level 3 LED, 100 lumens per watt. But if we were to find LEDs that met a tighter range of criteria for priority level 1 of preference, I don't know, maybe it's 60 lumens per watt. I'm making up numbers now. Another possibility is that we may find that higher priority levels cost more. Right? I mean, we're looking for a very specific set of LEDs at this point. So out of a given production run, it's possible that we're only going to get a small number that meet that criteria, and there's a lot of waste. Obviously, then the manufacturer is going to have to charge more money to compensate for that. That could also result in there being less availability. We're not really sure, but things to keep in mind, right? Okay, now let's look at some of the output from TM30 that we specifiers are going to find really useful. And that is the reports that are generated for us. So in 2015, we did not have a recommended set of values to report or a methodology for reporting them. After 2018 and these studies and the introduction of Annex E, we put together 3 different ways of reporting this information. Comes straight out of the TM30 calculator. The idea is manufacturers can just drop this into a cut sheet if they want to, or make it into a separate PDF, but get it up on their website, make it available for download very, very quickly. What we call the small report, or the simple report, is the color vector graphic. In the 4 corners, we have the 4 important measurements, RG, RF, RFH1, and RCSH1. Top right-hand corner, we've even simplified it for you. What are the PVF priority levels? The dash means that it doesn't qualify at all, so the numbers don't reach even the priority level of 3. Lower right-hand corner, we've got the CCT and the DUV, so that's useful information. And then the text there at the bottom is just saying to you that this was generated by the online version of this calculator using version whatever is up there. So when a report is made, it's tracking what the version, the TM30 version that was being used. We can give a little bit more information with the intermediate report, which adds bar graphs and numerical values for Chroma Shift and Hue Shift for each of the 16 hue bins that show up in the color vector graphic. So those numbers are in the arrows, right, that form the color vector graphic, but you can't look at those arrows and really draw numbers out of them. So this might be especially useful if, for instance, you've got a situation where you're curious about a single color or color range. If I'm lighting John Deere tractors, I'm concerned with green. These two bar graphs would let me go take a look at, is green being hue shifted and is green being chroma shifted? Fine. And here's the full page report, which we've added now a bar graph for the fidelity values for each of the hue bins. We've added the SPD of the light source in question, overlaid with its reference source. And across the bottom, we've got the fidelity values for each of the 99 color samples. So these are envisioned as being something like a quarter page, a third page, and a full page. Manufacturers can choose which one that they want to make available to specifiers. Let's now shift to talking a little bit about, as a designer, working with TM30 on a phase-by-phase basis, right? We all know what the phases of the design process are. I'm not going to even turn around and look at those. Now I'm going to turn around and look at this. Okay, so in schematic design, walls are moving around, ceiling heights are changing, ceilings are going from exposed to ACT to drywall, back to exposed. It's really hard for us at this point to be selecting fixtures. But we can do our basic research and our basic analysis and information gathering, talk to the owner, talk to the architect, talk to the interior designer, think about past projects, think about what this project type is, and make some conclusions about what our color rendering goals are for this particular project. And I think that that's something that can be reasonably accomplished in schematic design, even if you don't know where the walls and windows are yet. It's possible that we might also be able to prioritize, if we have more than one color rendering goal, what are the various priorities for those, or what are the various priority levels for those. That's a reasonable outcome in schematic design. You can put that into a narrative, send that off with the SD package, fine. So for instance, in a restaurant, we might talk to the owner, think about the project, talk to the architect, and we might conclude a few things. First of all, in this restaurant, we're going to use some sort of dim to warm technology. Great. In this restaurant, prices are high, it's in a fancy part of town, everybody is beautiful and everybody should look beautiful. In this restaurant, at $100 a plate, the food had better look beautiful too. Okay, so with these three ideas about what color rendering should do for our project, what might we decide? Is this a project where we're going to prioritize preference, vividness, or fidelity? I have one preference. I have preference. Yeah, I agree. If this was my project, I would say, okay, I'm going to start by saying I would like to find a P1 light source, and then we'll see what happens from there, right? Okay, different project. We're doing an office. Here's the ground plan. You can see we've got windows on 3.5 sides. So one of our early decisions is going to be we want a light source that's going to blend relatively seamlessly with all of that daylight that's coming in. Now, I don't want to necessarily have an exact match. I don't want 6,000 Kelvin light in the office, because people are going to work there when it's dark outside too. And in that case, it's going to be really awful. So I'm going to target a sort of a neutral CCT, 3,500 Kelvin. I think that'll work out fine. The other thing is that the corporate color is blue. The interior designer is using blue as an accent throughout the space. I want to make sure that I'm going to pick a light source that's not going to distort that corporate color. Okay, with that information, is my primary color rendering goal, again, preference, vividness, or fidelity? Fidelity, fidelity, fidelity. Yeah, exactly. I think that all of us would say, especially when we think about what's happening with the corporate color, fidelity is not necessarily our only color rendering goal, but it really is our dominant color rendering goal. Okay, so we move into design development, where walls have stopped moving around. We know what the ceiling height is. We're getting ready to, sort of implement our design ideas, start picking lighting fixtures. Where am I going to get this information? How do I evaluate various fixtures. In an ideal world, we would just go online, we'd go to the manufacturer's website, there'd be a TM30 report in the cut sheet. Or there'd be another PDF that I can click on and download the color rendering report separately. That is true with an increasing number of manufacturers, but not all manufacturers yet. Another thing that I might do would be to call my rep and say, hey, listen, I need a TM30 report for this fixture with this LED. I don't see it online. Can you get the manufacturer to send it to me? And that's a possibility, and hopefully, you know, we would get a fairly quick turnaround on that. I have had situations where what comes back to me from the manufacturer is a spreadsheet with the SPD. So I've got two columns, one that is the wavelength from 380 to 780, and then one that is the energy at each one of those wavelengths. That's fine, because I can go to the IES website, navigate my way to the TM30 calculator, say that I want to enter my own SPD. Over here on the rightmost column, just do a copy paste, enter all those values, and then press the button that says calculate. And I'm going to go to a new screen that's going to say to me, do you want to take a look at the simple, the intermediate, or the full report? And I can download those in a number of formats, right? PDF or a graphics format. And so it's all there. The other possibility, frankly, if you work for a firm that's got some spare cash and you're willing to spend $2,000 to $20,000, you can get yourself a Spectral Radiometer, but when you buy it, make sure that the software includes calculations for TM30. And today, oftentimes, the spectral information that's measured is able to be exported to a desktop app, or it's able to be sent up to the cloud, and there you're able to manipulate it and hopefully generate a TM30 report, or at the very worst, download the SPD, go to the IES website, generate your own report. We may at times find that we should be asking for more than one report, such as with dim to warm or tunable white. Because in this case now we're talking about a minimum of 2 discrete LED sets. So for instance, with a dim to warm, I've got a 3000K LED, I want that SPD. I've got an 1800K LED, I want that SPD, but I think I'm targeting 2200 for my restaurant, and so that's a blend of the two, and I can't do that in my head. So, you know, have the manufacturer mix to 2200, measure it, send you a report. And again, that shouldn't be that difficult. Okay, so we're working on this restaurant. We know that preference is our primary design intent. I'm going to sort of open the door a little bit because I don't really know what's out there commercially. I'm going to accept P1, but I'm also going to accept P2. In addition to that, and I'm going to explain to you in a little bit why, I'm also open to a P1 V3 or a P2 V3. And in terms of fidelity, I'll accept anything, 1, 2, or 3, as long as we're meeting one of those 3 specifications. And if that's the case, then all of these are viable contenders for me, right? So now we're reaching out to manufacturers, we're getting the SPD information, we're getting the TM30 reports, and we're saying, you know, okay, look, I got 6 fixtures that qualify. Let's start calling the reps, let's get samples sent over, let's take a look at these things, and in an ideal world, I suppose, let's use these to illuminate a color and materials board that the interior designer has given us, so that we're taking a look at the actual light on the actual materials. Great. In the office, same thing, right? I know that I want an F1. I'd also like to do better than just fidelity. I'd like to see if I can get also a preferred light source, maybe an F1 P1 or an F1 P2. And if that were the case, these 4 would all be acceptable to me. So again, as the TM30 reports are rolling in, some number of fixtures are looking like contenders. Let's call the reps. Let's see if we can get some samples sent over. In the office project, we have a supplemental concern, and that supplemental concern is the corporate blue. And the measures that are in Annex E The color that's specifically looked at is red, right? We're looking at red fidelity and we're looking at red chroma shift. It's not telling us anything about blue. But if we get the intermediate report or we get the full report, we're going to get information about that. In this case, blue is hue bin 11. So I can take a look at the fidelity of hue bin 11. I can take a look at the hue shift and at the chroma shift of hue bin 11. And in an ideal world, the fidelity will be near 100. The hue shift and chroma shift will be near 0. And under those circumstances, I can feel pretty confident that the blue is going to appear as everybody expects it to appear. Everybody knows what the company blue looks like, and that's what it's going to look like, and we're all good. Now, I said with the restaurant, we might be interested in a high preference, but also some level of vividness, right? And the reason for that is the Hunt effect, which says that as brightness decreases, the apparent vividness of colors also decreases. So if we've got a restaurant where dinner is going to be served at 5-foot candles, all of the colors in the restaurant are going to be muted versus dinner being served at 50-foot candles. Now, the studies that were done, the studies that are examined in Annex F that inform Annex E, all occurred between 20 and 70-foot candles. And this information, like what happens with colorfulness as light levels decrease, it's not some sort of a straight line where we can make a graph and then read what happens below 20-foot candles. It's just not going to, it doesn't work that way. And so what we're saying at the moment is we believe that probably, it's a lot of qualifiers, right? We believe that probably adding vividness at V3 or maybe at V2 if it's available is going to help to counteract the Hunt effect at low light levels. And so if I could find a P1 V3 or a P1 V2 dim to warm in my restaurant, hopefully at that 2200K that I was targeting, I'm meeting that V3 or maybe even that V2 requirement. And that's going to help to lift the chroma that otherwise is being suppressed by the low light levels. But I do want to emphasize, we don't have the research that guarantees this yet. It just seems like it should work. Yeah. And I just said all of that. Okay, so let's talk about CDs a little bit, and then we're going to go look at this great demo that we have. There's always a question of how do we hold our specification, right? How do we deal with substitutions? In some cases, it's really easy. I said that I wanted a 2x2, you're offering me a 2x4. No. But in some cases, we are pushed or we wind up having to shrug our shoulders and say, yeah, okay, fine. What can we put into our specification, or perhaps what can we put into our fixture schedule to help control for color rendering? The first thing might be simply this. With your submittals, require a TM30 report. You get the report in, you take a look at what the numbers are, you compare that to what your specified fixture was if we're looking at a substitution, and then you can simply say, no, the red chroma shift is negative 20%. This is terrible. I'm not going to accept this. Another way would be that we put that information into our fixture schedule, right? So we could put some information into our spec that says, see the fixture schedule, proposed fixtures have to match. And then, don't yell at me, I know everybody has a different format for their schedule, right? But let's say in your schedule you've got a cell for all the light source information. You can simply add a line that either for the PVF values, which is the simple way to do it, or you might have some reason to actually call out values and ranges, right? So in this case over here, this is essentially a P1 specification, but in this project, we've taken the approach that we are not going to accept a reduction in red chroma, right? So P1 lets the RCSH1 be -1, we're going to say no. It's a minor thing, but we're going to make it be 0 or positive. And you can just put the values in there. I mean, that's entirely allowable. The other possibility would be to just set global requirements for the entire project. And this is, for example, what the Department of Defense has in their design document that sets requirements for healthcare facilities. DoD healthcare facilities throughout the world have to meet this. So, okay, fine, you just put this into your specification, and then any fixture that you get, you can simply look at the TM30 report. If it doesn't meet these requirements, it's rejected. Done, right? And so we can come up with strategies where hopefully all of the time, most of the time, much of the time, we can defend even our color rendering goals, right? And how those are brought into a project. So I'm just going to close with, since 1965, color rendering has essentially meant color fidelity because that's the only thing that we've measured or been able to measure. That's not the case anymore, and there are a lot of problems with CRI. Tony touched on a couple of them, but today, really, we all ought to be moving to TM30, which is the most up-to-date, the most accurate, by far the most flexible color rendering evaluation system. And we would all do well to bring this into our professional practice just as quickly as possible. And if and when you're ready to do that, reach out to me, reach out to Tony, reach out to anybody else on the IES Color Committee. We're all really passionate about this and we'll help you, okay? Questions before we run into the demo? No, yeah.
I'm a manufacturer, and do you guys like seeing the TM30 stuff on the spec sheet? Because my customers do the whole thing in the spec sheet from this middle, ends up being from 10 fixtures to 100 pages long.
Yeah.
So
Pull some of your specifiers about. My preference, because I only want to download and track one document, I want it in the cut sheet. But I know a number of manufacturers who are showing it as a separate download, quite possibly for that reason. They don't want to have 20-page long cut sheets. And I understand that. I don't want to have 200-page long specifications. So yeah, there is a trade-off, and I would say, you know, I mean, it's just ones and zeros, right? Once you have one of each beta, they're uploaded. Yeah, then your specifiers have the option of picking either one. There's a lot of flexibility in how you want to show that information, right? I mean, starting with, do you want the small, medium, or large report? We leave that entirely up to you. We're not trying to tell a manufacturer what or how to do this. We're just encouraging them to make the information available in a way that they think is most appropriate, you know, for their customers. Well, when you do that, you got to get TM30 in there as well.
source. Looks like there's some space over there, so if you're cramped over here. All right, welcome to the live demo portion of this session, where we show you that we're not making the Dallas Center has been critical in helping us put this together, so they helped us put together this whole vignette and plan for our friends to be here. So, yeah, so let's jump right in. So, we're going to show a lot of data on the slide. Hopefully some of this will look familiar now after having seen the first part of the presentation. Some of the big pieces of information to pay attention to. Color vector graphic up in the top left-hand corner. Right, so we can see specifically how the light source that we're going to be looking at increases or decreases the saturation of objects, right, relative to the reference illuminant. This is, again, the high-pressure sodium that we looked at earlier, right, so we can start to familiarize. And then the top right-hand corner is the Annex E table that Jason talked a lot about. So we can see, for example, that our high-pressure sodium doesn't achieve any category. It's all grayed out because it's a terrible light source, right, in terms of color rendering. And so focus on any part you want. Those two are going to be the real big ones. So we'll start with a question and ask, is the specification of RF greater than 80 a reasonable specification? This might be equivalent to roughly the status quo of a CRI 80 spec. Maybe a little more strict, but really, really close. So what do we think? Reasonable, not reasonable?
Depends on the application.
Depends on the application. That's a good answer. Yeah, good answer for sure.
Okay.
And so, yeah, that's a good answer. So, well, let's look at a couple things at RF 80. So, I'll bring up this light source with an RF 80. Okay, if we look at the color vector graphic, if we don't have a sharp or keen eye, we might try to compare what we're seeing to the color vector graphic. This is a RF 80. You can see that it's slightly quite a bit desaturates the colors of red, so maybe this red dress doesn't look quite as red as it could look. It increases the saturation of yellow, so we can see that the dress is quite a nice lemony look. Our apples and our oranges are a little desaturated. Our skin tones are a little desaturated, more onto the duller, dimmer side. But importantly, we can have a light source at RF 80 that looks like this on the screen that increases the saturation of reds and is a P1, a light source with the same fidelity value but that people really like. And I'm going to show you that in a second. And the biggest drastic change, because the current one is a desaturation of reds, is going to come in the reds. So pick a place to focus as the transition happens, either in the red, orange, yellow, or skin, and I'll make the transition in 3, 2, 1. So this is a highly preferred, this is your P1 top of the range light source, right? This is, so same RF as the previous light source, drastically different impacts on color perception. So at the same RF, I can show you a light source now that drastically desaturates reds, all with the same RF value, okay? No PVF category because it's a really poor light source. And I'll show you that in 3, 2, 1. Drastically desaturates colors. Makes our yellows a little muddy. Makes our food a little less appetizing. And so if we write a specification for RF 80, even depending on even in any application, we can have all three of the light sources we just saw. But hopefully you agree that they're not all equally as attractive. They're not all equal among other dimensions of color rendering. So just to compare them directly, I'll show you side by side these two light sources. Both with RF 80, high preference, high preference, undesirable. Right? You can see the reds coming alive and dying, our skin sort of coming up in vibrant and blushing, down to yellow and dim. And we see our food coming up to light, the reds and the apples and the orange, and then coming down. This is $1,000 dress. This is clearance rack. Yeah. Right? So this makes a big difference in how we perceive these objects. So we can say, okay, well, if maybe RF used alone or color fidelity measure used alone is not reasonable. What if we had gamut area, right? What if we just use these two measures? We had gamut area greater than 100. Is this a reasonable spec? Well, I mean, maybe it's at least more reasonable than just RF80, right? So we can explore what that is like. So I'll bring us back to one of the light sources we saw a bit ago. RF80, RG100, it's still desaturating reds. Okay. Now I can show you a light source, the same RF, the same RG, and opposite impacts on color perception. So on screen, at the same RF and RG, we can have a highly preferred light source that increases the saturation of red. Okay? And I'll show you that light source. Pick your focal point in 3, 2, 1. Same RF, same RG, opposite impacts of color. We can show those side by side. High red, low yellow, high yellow, low red. Do you see that? No. So importantly, we can ask, both of these meet the same spec, but which one, if you wrote this spec, do you think you would get?
Gotta check out that TM30.
The truth is you would get this one, the one that desaturates reds. And the primary reason for that is because light sources are typically optimized first for efficacy, for lumen output. And the sensitivity curve for lumens peaks in the green. What happens when you increase green? You pull back red. Okay? And so there's a bit of a tug of war between efficacy and red rendition. But what's important is we can see that optimizing for red rendition is equally as important, right? And so optimizing only for efficacy results in getting this light source when you could have this light source. So in the monolithic world of color fidelity, we might ask, is RF95 a reasonable color rendering spec? What's that?
You would think so.
You would think so.
You got all
Okay.
the trick questions, Tom.
I try to keep you on your toes, you know? So, we can evaluate that. So, here is RF95. If all you care about is color fidelity, right? This is the cream of the crop. This is the gold standard that you're looking at, right? All you care about, and you only live in the monolithic world of color fidelity, this is the best you can do. And if that's all you care about, you may spend most of your career trying to get these 95 or RFs on all your projects, right? But I think the answer to the question is this is reasonable. This is things look good. Skin looks good. The red dress looks good. The yellow dress looks good. It's reasonable. The food is edible. This is a fine light source, right? Like as Jason said, we're not here to tear down the walls of fidelity and throw the baby out with the bathwater. You know, it's not bad. It's just not the only thing. And so what we can show is compare this to a high preference light source, one that increases the saturation of reds, and which will create a perceptual difference even compared to this very high fidelity light source. So I'll show you that in 3, 2, 1. And then I'll switch them back and forth. High fidelity, high preference. High fidelity, high preference. Okay? So, again, not trying to get rid of fidelity altogether, it's just there are other things we can do. Alright. So, as Jason mentioned, when we get into the world of vividness, we can push vividness so high that things start to look pretty crazy. And there's this sort of trade-off where we can increase and increase saturation, and people say, I prefer it, I prefer it, I prefer it. Until you get to a certain point, and the preference starts to fall off a cliff. Right? And so we can get so saturated that people don't tend to like it. And so we'll show that Now, so this is going to be a nearly V1 light source. So it's only not V1 because the gamut area I think is a few points too low, but otherwise the saturation is correct for a V1. So 1, 2, 3. Can you see that? Sort of jumps off of the mannequin. You can contrast that to, again, a light source with the same color fidelity and drastic desaturation of objects. Especially specifically at red. 1, 2, 3. And then super vivid, super dull. Some things to look at, obviously the red and the yellow, skimmed. The Tide box is one I really liked. Sort of crazy. The red food stuff sort of jumps off the shelf. Some of the purples and the blues.
Yeah, it's made of soup cans.
Yeah.
So one of the reasons that all this really matters is that our eyes very rapidly adapt to changes in color. We don't see incandescent light as amber. We don't see daylight as blue. It's white. But our visual system does not adapt to poor color rendering. If we're looking at this, we see this, not this. This, we see this all day long. This is the light that we have to focus on. Our visual system is not going to adapt.
Yeah, that's a good point. Yeah. So I have some other cool stuff to show if you're interested, but this is sort of the end of the TM30 portion. So if you have any questions about what you've seen so far. They're all, I believe, 3000 Kelvin at 300 lux on the surface of the merchandise. Yeah, yeah. So they're all same CCT, same illuminance. Insofar as we're able to keep them the same, you know? Yeah. But, yeah, so all
Are
of,
the sources the same?
what's that?
Are all the sources the same, or some incandescent, some are?
No, they're all 7-channel LEDs.
Okay.
Yep.
Got it.
No incandescent.
Okay.
Yeah. And I can show you that in a second.
Uh-huh.
Walk through it. It's pretty fun. So, yeah, but no more questions about that. I'll show you something. Yeah, go ahead.
So you're using this in practice, right? You are feeding the TM30 data and trying to figure out, hey, this source is better than this source or this data. In today's world, it's not a source, it's a fixed data. It's not all together. And so is the data still get to these rows in your head? Look at the data. So when you are very accurate, you take one red light to realize, or when you turn it on and realize that it's been a surprise, kind of asking you as the expert to look at it for a certain reason.
I wouldn't say that it's very accurate. Insofar as, is there a difference between RF 71 and RF 51? Can you see that? Yeah, maybe not. So what I'm looking for is sort of a bigger color of, there's a particular color that I want to make sure I get that as well. Or there's a particular color that has okay distortion. Or I have a gold preference, or I have a gold preference, or I have a gold preference. And so, yeah, I'm working in larger gestures, not within, at least until I get samples. Right? Then if I've got sample A and sample B, now I can really see what's going on.
Right. But at that moment, it doesn't matter what the browser is saying. It's
Exactly.
something that
Yes, exactly.
What I would say though is like somebody who's programmed these things hundreds of times, right? I think if you've got the right data, right? So if you're trying to evaluate a picture but you have chip data, right? Or vice versa, not good. But if you have a fixture that outsets the spectrum and you have this TM30 data for that, I believe that with experience, there is intuition to be developed. right? Like as Jason's point, you're not going to be able to necessarily imagine the difference between a Chroma Shift of +1% and +2%. But if you were looking at this light source, you for sure can develop an intuition that it's going to look like that, on the sort of more of the magnitude scale than the decimal scale, right?
Right, yeah, that's a good way to put it.
Yeah, and so for sure I do. Like I can, like if I look at these two on a spec sheet, I might not be able to pick up all the different colors in my mind, but I know that they're going to roughly look like this. Yeah.
And you definitely know that if the red Chroma Shift is negative 19%, nothing's going to look good with this light source.
Yeah.
Are there any study about retail lighting? Because this is a game changer for retail.
Yeah, we've had that come up a couple
Yeah,
times so
you know,
far.
I think there are two answers. One answer is that there's a lot of studies on retail lighting that have been done over the past, let's call it 20 years. More have been done in Europe than in the US. And the problem is that the information from those studies just doesn't penetrate professional practice. So if you wanted to know what studies existed that might inform professional practice, I don't know what you do. You start at Google Scholar and type in retail lighting and see what Google Scholar can serve up to you. But as Tony has said so many times over the years, it's really hard to find research into this kind of thing. And so, is there evidence that a P3 or let's say a P1 is going to result in higher sales than just an F1? No, there's no evidence.
Yeah,
I mean, does it seem like it should? Yeah, but we can't demonstrate it.
Not yet. Hopefully we do eventually. These studies are actually also difficult to do, right? So they take a lot of care and consideration and time and input from multiple people, including the lighting designer, the scientist, the people installing the lighting. If you're doing it in a real retail space, there's a lot of other complicating factors. So these are hard studies to do.
I think it's like an example of what could happen is there's a very well-known study where Walmart wanted to know if adding daylight to their stores would increase sales. And from some number of stores, added skylights to the existing stores, and saw the sales, increase.
Yeah.
And
Now they all have skylights.
now they have skylights. But like, is Walmart going to do that with color rendering?
Yeah, it's hard to know.
So if VOE is right and LEDs are going to transition from phosphor converted white to color mixed white, they'll basically be like demo lights.
In theory, yeah.
How will you have a TM30 report? Like, how could you do a TM30 report on something like this?
Yeah, so that's a good question. So I think even if you get to a point where creating a color mixed LED is more efficacious than doing a phosphor converted solution, I have a feeling that manufacturers are still going to sell them with pre-mixed points, right? It's not going to be a guitar. It's going to be a song, right? It could be a guitar.
Especially for circadian or something.
It could be,
But
yeah.
then what happens is that finally, your control system needs to know the SPD and do the math. The spectral power distribution of each one of those LEDs and be able to do the math on the fly for you. So
For any combination.
Yeah, so that you say, for starters, show me a B1.
Yeah.
And then at that point, and you can do it on stage lighting control consoles. You can say, great, hold that, but a little bit more red. And it'll hold the color point, but it'll adjust everything else so that you get a little bit more red or a little bit more green. That's really, really complicated. And at the moment, only exists in stage lighting.
Thank you for coming.
Thank you.
We're past our time with them. So.
So it's not that it's impossible, it's just nobody's taken on that challenge.
The controls will be a huge part of that, right? It's like not just the ability to do math on the fly and quickly, but an intelligent user interface that allows you to tell it what you want, right? And then a knowledgeable user who knows how to tell it what they want, So
But I think the way to be a knowledgeable user of all that is to understand this. Right, to understand how changes in the SPD are going to affect, color perception. If you don't know that, then you're just stabbing at buttons.
Yeah, but there will no longer be the trade-offs that we see in some way.
In theory, yeah. Well, I hope that's true because things will this will be easier to achieve. Yeah. So I'll show you one thing. One cool thing that Jason and I discovered while we were programming here. So one of the cool things that happens with really short wavelength energy, sort of like in your 380 to 420 nanometers, is that they fluoresce. They cause light chemicals to fluoresce. And so a lot of manufacturers put these fluorescing agents into their products to make them more attractive, to make them look brighter or whiter. Yeah. And so we happen to have one of those short wavelength LEDs in here that excites one particular thing that we'd like to show you is watch the gain box. So we were programming and that happened and we were just blown away.
Wow.
Yeah.
They know something,
The other
right?
product we're talking is the yellow shoes over on the right. This morning we had a model, and it turned out there were fluorescent agents in her nail polish.
Yeah.
Yeah.
Yeah. So we thought that was really fun. And then if you want, we can show you just all of the different channels of the LED. So these are red. Stare at long enough and feel like you're in a different planet. There's amber. There's lime. There's green. There's blue. Yeah. This.
Amber is like the more comfortable one, right?
Say that again.
The amber feels like the more comfortable one.
Yeah. So some of these LEDs are individual diodes of color, and then some of them are actually phosphor converted. Amber has a broad spectral distribution because it's a phosphor converted. The same with lime.
Okay.
And so the other ones, like this one, is just a direct blue. Yeah.
Almost a vertical line.
Yeah,
Yes,
very close, especially in the chromaticity diagram. Yeah. And then you have the indigo. Yeah. And then the last one is cyan.
These are 7 channels.
Yep. And then all of them on at the same time. It's super bright. Yeah. They're much more powerful than what we're using them to do.
And the red looks good.
Yeah, so all of them on, this is probably like a pretty high CRI light source, like high color fidelity, high RF. Trying to use all of the names, right, to create the association, you know? But yeah, all of them on. So yeah.
So how do you program that particular action?
So what I do is, it depends on the fixture. So if I have my research fixtures, I can control the individual LEDs by like 1% increments. And so I do the math and I say, I need my red to be 50%, I need the green to be 10%, I need this one. And then I create that mixture, I put it into the fixture. It's never perfect on the first try. Then you calibrate it. And
So
then
you're basically measuring it with
a spectrometer. Yeah. With these, it's a little different because they're not research grade fixtures, so it's really difficult to get direct individual control of each channel, right? Because these are meant for they have end users, right? By research fixtures are meant to be used by a researcher and messed with. These are meant to be. They're designed to be easier to use, right? And so there's some software that allows you to, like Jason said, if I want to change the color but hold my color point, all I got to do is drag and drop, and it'll keep it the CCT the same by changing the colors. So how I did this is with that software and just basically messing with it enough times to learn what I needed to drag and drop around to get to the color corrected graphics. And so, yeah, so these are all actual measurements. So they're not. So these are actual measurements of the things you're seeing. So you do the tweaking, you measure, and you tweak until you get it right, and then once you save that setting, then that's what you use. Yes. Thanks. And that's the
Have like a way of time there, standing there.
Yeah. It depends on the software. All my spectral measurements I put in that, so I can do all my computations. But like if you put the SPD into Tm30 Calculator, it will give you all that information. Yeah. But if you're programming it yourself, you got to program it yourself, right? So.
Can I ask you, well, I mean, I got a portable lighting passport, but does you all do that separately, you think, or?
The lighting passport, so...
with like, when I go and get my in situ test and the sphere and the gonio, I'm getting that whole rundown.
Yep.
Do you know if I have to ask for that? I mean, that was
It
something
depends
you
if
all
the lab
asked.
will calculate it for you, right? So all you need is the SPD. So if you're already getting your CRI value, right, then the